Hi, everybody. I am recording. I have the recording started. So I know it's been a while since I've conducted a live class with this group. I'm going to try to do more of them because remote learning, it is tricky with the videos. Uh, I have noticed that um, I'm not getting like so many people submitting assignments on time. Like for instance, it was only out of the 12 people, I think 8 people submitted the last assignment. Now that might be the people who are also here in the in the in the room, in the Zoom room. But just want to remind you, we want to get the homeworks in 9:30 on the day of the next class. And just to remind you that in regular times, this class would be like 5 hours of time a day. If you think about it, probably have an hour to get to City College, depending on where you are. The class was like 3 hours. There's a break in the middle, an hour to get home. That's just 5 hours right there. And then the homework was probably another hour. So you want to dedicate time, all that time that you would be commuting, you want to dedicate that. Think of that as earned time that you work. Now, you might have a lot of other things going on in your life and you're watching your kids and things like that. So I'm not saying that it's easy, but if you are doing the assignments on time, keep doing that. And if you're not, would you start doing that better? Okay, now we are into our third culture. The first few days were about Babylonian math. The next couple of days were about Egyptian math. And these next couple of yesterday or the last class and what we're doing today and tomorrow, and at least 3 days on math from China. And the math from China is more recent than the math from the Babylonians, who are like 1600 BC, and the Egyptians that are also like 1600 BC. Most of the math from China that we know about comes from a book called The 9 Chapters of the Mathematical Arts, which was a book that was compiled from about 500 BC through around 500 AD. So we're talking about a 1,000-year process of writing this book and refining it. The Pythagorean theorem questions, which for them was called go problems, those were all in what's called chapter 9, so the 9th chapter of the 9 chapters. But today we're going to look at another thing. Now, this is the one thing in Chinese math that is actually named for them. In other words, even Pythagorean theorem, we don't call it the Go theorem. They do in China, but we call it the Pythagorean theorem because, in the Western world, someone like Pythagoras gets credit for it because of, that's what happens in history sometimes. Someone gets credit for inventing something that they didn't really invent. But at least for China, the Chinese remainder theorem is something that's just what it's called. I mean, there are other things like Pascal's triangle was invented in China, but we call it Pascal's triangle. But Chinese remainder theorem is called the Chinese remainder theorem by all mathematicians. Everyone knows that is what it's called. So in doing the math of China, we definitely want to study the Chinese remainder theorem. The Chinese remainder theorem is a series of problems where you're asked to find a mystery number. And the given information is, in this case, you could look at this question, what's given is that if you divide, they tell you what remainder you would get if you were to divide the number by some other number. So they say in this one, what's the smallest integer that leaves remainder 5 when you divide by 13? Now that piece of information on its own, that has an infinite number of answers, remainder 5 when you divide by 13. but it also has a remainder of 13 when I divide by 17. And that in the green has an infinite number of numbers that would make that true. And there's also an infinite number of numbers that make both conditions true, but there is only one smallest integer that makes both of the conditions true. And just through like messing around and trial and error, it's not a very large number. Does anyone know what it is just because they messed around with the numbers? You can play around with that for a minute. Anyone making a list of numbers that satisfy the first condition? What are the smallest numbers that make the first condition true? Why don't we have someone type that into the chat? Name 5 numbers that make the condition that's highlighted in yellow true. Would someone in the chat type in at least one number that makes the yellow condition true? An integer that leaves remainder 5 when I divide by 13. So that's if you divide the other way. If you divide, I guess what I'm getting at is like when you divide by 13, you want to get remainder 5 like that. I know this word leaves, maybe that's not like the most accurate number, but 8 divided by 13 gives you remainder 5. But 31 is an example because it's 2 remainder 5. And what's the smallest such number that gives me remainder 5? 18. Now, if I made a list of all the numbers, what's sort of the difference between these two answers? Like if I wanted to make a list of all the numbers that make that get me remainder 5. Like what would the next number be? If 18 is the smallest and 31's the next smallest, what would be the next question? That's right, it's got a difference of 13. So I could actually make a list. I could add 18. I could add 18. I could add 18. And I could keep doing that. This would not be the most efficient way for doing that. And I see there 13n plus 5. That's right. Every number is 13 times something and then plus 5, where n is an integer. So I could do the same thing with the green. If it's remainder 13 when I divide by 17, the smallest number would be 30. And that list would be 30. And the next one would be 47. And yes, I see 13n plus 5. So I could, in theory, make these lists and just find the smallest number that's on both lists. The answer would end up becoming, just so you know, the answer would end up becoming 200 at the end. 200 would be on both lists. You can see here 200 divided by 13 is 15 remainder 5, and 200 divided by 17 is 11 remainder 13. And 200 is the answer to that question. And the goal of today's lesson is to show you an algorithm for calculating questions like this, and not just doing it when there's two like conditions, but sometimes there's three conditions. So I might say, oh, also has to have, remainder 2 when you divide by 11. And now suddenly 200 doesn't work because it only satisfies 2 of the 3 conditions. So that's called the Chinese remainder problems. Has anyone encountered this problem in a math course they took already? What math course, what field of math is this in? It is number theory. And it's interesting that in China, they have this early number theory. Now, these questions, sometimes they came up as word problems. There's an example, they'll say like a general has, we don't know how many soldiers the general has, but when he lines them up in groups of 7, there's 2 people left over, but when he lines them up in groups of 10, there's 5 people left over. How many people are in the army? And these word problems are definitely like recreational. It's not really important to know that. That's not any information anyone would know about an army. You wouldn't say, oh, there's an army coming, and I noticed that when they were lined up in groups of 7, there were 2 people left over. When they were lined up in groups of 10, 5 people left over. How many people are in the army? No, you just count the people in the army. But there is some speculation that problems like this could be important in one application besides like fun word problems, which is astronomy. Because like if you have the sun here, and if the Earth goes around every 365 days, and then you have another planet, you have Mars, different planets, different things in the sky. Well, in relation to us, things appear in the sky at night at various intervals. Like Mars might be lined up with Earth like that, so we see it at midnight. Once every, I'm just going to make up a thing. I'm going to say once every 580 days before Mars is like straight up in the sky at midnight. And maybe Earth and Jupiter are lined up in this way once every, 750 days. And maybe I want to know like, when is it going to be that like Mars is here and Jupiter is here? Well, that's kind of like a remainder question, because if they're all lined up, let's say at the day we're starting, if every 580 days they line up again, then it's going to be over here. Let's say that Mars moves from here to here in relation to us, every 20 days. They'd be asking, well, that was the remainder, because every 580 days is back to this position. So I want to know, when will it be here? Well, that's when will it have remainder 20 when I divide by 580? When will Jupiter be here? Maybe this thing happens every, 1,000 days. So anyway, what I'm getting at is that there is a potential scientific application of Chinese remainder theorem, and it's not just about riddles about numbers or generals lining up their armies in rectangular grids. So just wanted to let you know that. The Chinese remainder theorem first appears in 250 AD. We see this question. There's a book called Master Sun's Mathematical Manual. And it says here, there are certain things whose number is unknown. A number is repeatedly divided by 3, the remainder is 2, divided by 5, the remainder is 3, and by 7, the remainder is 2. what will the number be? That's the first time we see this. So this question, and let me give you a little bit of notation now. Remember this warm-up question? A fancy way of saying this in number theory, if you ever see this like 200, 3 equal sign, 200, triple equal sign, 5. That's the fancy way of saying 200 divided by 13 has remainder 5. It's a little more sophisticated than that, but for our purposes, we'll think of this as the remainder when you divide by this. Now, I will sometimes put the mod here and use a regular equal sign instead of this triple equal sign. That triple equal sign stands for congruent, and it's not exactly the same thing as equal, but for our purposes. So I might say this, because this is sort of more natural to think, oh, well, 200 divided by 13 is remainder 5. So we could write this question as x mod 13 equals 5, and x mod 17 equals 13. That doesn't help you answer the question at all. That's just a shorthand way of writing the question without using all those words. Okay, so prerequisite is that you've studied modulo already. Great. So this is our way of phrasing the question. If you prefer, because it's a little more accurate, to use the 3 equal signs, the congruent sign, and you want to say x is congruent to 5 mod 13, because the 13 actually applies to both numbers. That's better. That's like more official. Now, they give a hint. Here's back to the Master Son's mathematical manual. Oh, actually, they don't give the answer here, but here's the question worded in modern notation. This one's a pretty small number. Anyone want to just say, so we have like a fun one with 3. We want to get x divided by 3 is remainder 2. If I divide by 5, I get remainder 3. And if I divide by 7, I get remainder 2. And when we mess around, it's a fairly small number. It's always less than the products of the 3 things you're modding by, so it's less than 105. And we know what the answer is, then we could learn, we are going to learn a method for solving it. Anyone have a thought about? One hint is that I think if you start with what numbers leave remainder 3 when you divide by 5, you will come upon the answer pretty quick if you just list out the numbers that remainder 3 when you divide by 5 and just check, do they satisfy the other 2 conditions also? Who wants to put into the chat what the answer is? It's a small number. It's not very large. What can you say about the number just based on this condition? Just based on the middle condition. What types of numbers? Well, eight is the smallest number that makes that condition true. And what can you say about all the numbers that make that condition true? It has to end in a 3 or an 8 is correct. So if you look at all the numbers that end in 3 and 8, 23, 28, 33, 38, it is going to be one of these 6 numbers. Which one works for the other 2 conditions also? Because this is a system of equations, or yeah, it's like it's not 3 different answers. One answer that makes all 3 things true simultaneously. So which of these 6 numbers also satisfies the other conditions? That if you divide by 3, you get remainder 2. If you divide by 7, you get remainder 2. Well, 18 divided by 7 would give remainder 4, because it would be 18 divided by 7 is 2, which is 14, which would be remainder 4. So it can't be 18, but it is 23. 23 divided by 3 is 7, remainder 2. 23 divided by 5 is 4, remainder 3. 25 divided by 7 is 3, remainder 2. Now we are going to get a process for answering these questions. And if you took number theory, you might have learned a process, but it actually would be a very lengthy process, except I'm going to let you do a shortcut for the hardest step, the lengthiest time-consuming step of the process, where you can use a chart for it. And if it's not on the chart, I'll let you use Wolfram Alpha to do the hardest, most time-consuming part of the process. Okay, what we're going to need is a chart. And here I have and by the way, this is on the document. Not only is this on the document, the Google Doc, but I also have the filled in column on the Google Doc also. But let me show you what this chart is and how it will help us. What I have here is I have rows that are prime numbers, 3, 5, 7, 11, 13, 17, 19. And I have columns that are the same numbers there. And what these numbers are inside, this is a little cryptic, this 2, 5, 4, 9. What those numbers are, let me just focus on one of the numbers. So why is there a 5 right there? Well, there's a 5 there because if I take 3 and I multiply it by 5, and I mod that by the number here, which is 7, I will get 1 as my answer. So 3 times 5 is 15. 15 divided by 7 is remainder 1. And that's what all these numbers do. They get us remainder 1. So the reason there's a 9 here, there's a 9 there, because 3 times 9 is going to be congruent to 1 mod 13. And you can test that. 3 times 9 is 27. 27 divided by 13 is 2, remainder 1. So the numbers in this chart are numbers that will, if I multiply the number in the chart by the column that it's in, and I mod it by the row it's in, I will definitely get 1 for each of those. Now, finding that number is pretty tricky, but just to have fun and see if you're understanding the process, would you take a minute to ponder what numbers should go in these, what numbers should go in, oops, that's I'm going to change the pen. Hold on. That pen was already good color. Put the highlighter, that's what I want. Take a minute just to mess around with these 4 boxes. What should go in those 4 boxes? And you could do it by trial and error. We don't need fancy math for this. Just to make sure you understand what the numbers in this chart are even trying to do. When someone gets the very first one, type it into, yes, I see 2 is the first one. 2 is correct, because 5 times 2 is 10, and 10 divided by 3 is 3, remainder 1. So that number is not the remainder. It's the number that would cause you to get remainder 1. Let's get this second one, the 5. This one here with the 5 and the 7. Yes, that one is 3. And that's because 5 times 3 is 15. 5 times 3 is 15. 15 divided by 7 is 2. Remainder 1. Now you could get all of these through eventually trial and error, but I filled in the chart here, and you have the filled in chart in your in the document. So you want to have it handy because we're going to use this chart to help us. You don't need to copy the chart. You could just have the chart handy. Again, if you get the Google Doc up, you print it out, or if you just have it in a window on your screen, you can reference it. Here's just a question in general. So like these numbers here are basically saying 3 times what is congruent to 1 mod 5. That's how, you know, that's where this number comes from. Does anyone know from number theory what it's called when you're trying to find 3 something times what is equal to 1 specifically, trying to get a 1 there? What that's called in number theory? What if it didn't say mod 5? It just said 3x equals 1. What would x be then? Then it would be 1/3. Well, we can't use fractions in mod, so this one's not 1/3. It's 2. What's it called when you do that? Yes, it is the inverse. We say 3 inverse is equal to 1 in mod 5. Inverse. And inverse is a really important concept in number theory. So check this out. If I'm gonna, let me just share my screen for a second. Here's Wolfram Alpha. And if you type in 3, this little raised to the -1 mod 5, and hit enter, it does get you the answer. So I will let you, if you get a situation, we need a number that's not on the chart because it's using like not 3, 5, 7, 11, 13, 17, 19, but bigger numbers. Or if you have to fill in a number in the chart, I will permit you to use Wolfram Alpha to do this. I find the one weird thing about Wolfram Alpha, if I wanted to do like 10 inverse of 10, you know, mod 13, I might get an answer of 4. 10 times 4 is 40. 40 divided by 13 is 3, remainder of 1. But for some reason, if I put like like 2 times 5 here, then it doesn't work anymore. Like, to me, that should work. That should get me the same answer. 2 times 5 is 10. But I guess, listen, Wolfram Alpha knows what they're doing, and they purposely made it that it's not. There's some subtle difference between those 2 things. Oh, somebody asked about the 3 and 8 from before. Sorry, I didn't see that. Well, if you get no remainder when you divide by 5, you have to end in a 0 or a 5. So to get remainder 3 when you divide by 5, you have to be 3 more than a number that ends in 0 or 5. So 3 more than a number that ends in 0 ends in a 3. 3 more than a number that ends in a 5 will end in an 8. Okay, so you can use this. I permit you to use Wolfram Alpha. Just be careful. It only works the way we expect it to if there's a regular number there and not some kind of expression. Okay, so let's see. What good is it to have this chart? How is that chart going to help me answer Chinese remainder questions? Well, that's coming right now. No, don't worry about that. Hold on. You know what? I think I'm going to use some of my lesson got a little, wasn't as, I'm going to use the actual example that we did for the warm-up question. So I would like to go back to the warm-up question, which was 5 mod 13 and 13 mod 17. And we know the answer is 200 because I already told you the answer is 200. But let me take you through the algorithm now and show you how this chart will be crucial to the algorithm. And then I'll show you how we can even do, if there's 3 conditions, but we need a different chart for that. Okay, so here we go, everybody. And pay very careful attention to this. I am going to make 9 sort of slots that numbers are going to go on top of. And when I fill in these 9, when I see these 9 numbers, when I fill in these 9 numbers, I'll be done with the question. I can calculate out. And I'm going to be a little cryptic and just show you first what the process is and then analyze why it works instead of like deriving it as some kind of like theorem or something. Over here, I'm going to put 17. Over here, I'm going to put 13. Those could be interchanged also. Over here, I'm going to put both. So in 4 of the 9 slots, I have these mod numbers. Now, the most important 2 numbers are going to be what goes here and here. Now, this first one, and these are both going to come from the chart. So to figure out what goes in this spot right here, I'm going to go to the chart, and I'm going to look up. I have 17 and 13 are my 2 mod numbers. I'm going to go here, and I'm going to go to the 17 row and the 13 column, and I have a 10 there. So that means that 17 times 10, which is 170, mod 13 is equal to 1. And it's true because 13 times 13 is 169, which is 1 less than 170. And that 10, I'm going to put right here. Now, for the other number, this one, I'm going to do the same thing, but this time I'm going to go the 13 column and the 17 row, which is the number 4. 13 times 4 is 52, which is 1 more than 51, which is 17 times 3. And now I'm going to put for the next two numbers that I fill in, which is this and this one and this one. These are going to come from the remainders. So I'm going to put the 5. Now you might say, why don't I put it with the other one? Well, for remainder 13, I'm going to put it into the 3 numbers that does not have the 13 in it. And the remainder for 17 is going to go over there. Now this may seem kind of weird. Why don't I put the 5 with the 13? It's going to make sense after. I'm sorry, why don't I put the 5 with this 13? I'm not explaining yet why this is working. I'm just cryptically assembling 9 numbers. I have 8 out of the 9 filled in already. Now, just to see where I am with this problem, because I have 6 numbers filled in, if I do 5 times 10 times 17, I get 850. And if I do 13 times 4 times 13, I get 676. And if I add those 2 numbers together, I get 1,526. Now, I'm going to claim that 1526 is, well, it's not 200. It's not the smallest answer that makes the 2 equations true, but it is something that does make both equations true. But it's kind of big. Let's see why that is. How do I know that 1526 makes both equations true? Well, look at this expression. I'm going to put it on its own page. 5, 10, 17, 13, 4, 13. I'm going to write it twice. This number, which we know is 1526, but let's say I didn't even know it was 1526. I just have it written down in this form. If I take this whole number and I mod it by 13, sorry. If I mod it by 13, this thing will become 5. How do I know that? Because this is the real important part, 10 times 17 mod 13 will definitely get me remainder 1. But then when I multiply it by 5, it will get remainder 5. How do I know that 10 times 17 will get me a remainder of 1 when I divide by 13? Where'd the 10 come from? Oh, I lost the chat. Hold on. How do I know that this part, I know that's remainder of 1 when I divide it by 13. How do I know that? Yes. That's what the chart did. That's the whole purpose of the chart. So that thing would get me remainder of 1 when I divide by 13. So when I throw this 5 onto it, it now turns to remainder 5 when I divide by 13. That piece. But what happens to the remainder when I add on this thing and divide by 13? What happens when you add a multiple of 13? What happens to the remainder? It doesn't change. That's right. So because this piece is 0 in mod 13, there's actually two 13s here, that's just coincidence. But I think if this 13 causes, when I divide by 13, this thing doesn't contribute to the remainder. The only thing that matters for the remainder is this thing. Well, that thing is going to be remainder 5 because this is going to be remainder 1 because I pulled that 10 off the chart so that 10 times 17 would be remainder 1 when I divide by 13. Now look what happens down here. If instead I do mod 17, this thing won't contribute to the remainder because it's a multiple of 17. So whatever the remainder of this thing is when you divide by 17 is, it'll be the same thing when you add on this 5 times 10 times 17, the remainder won't change. But what's the remainder when this 4 times 13 is divided by 17? You type it in. What's the remainder of 4 times 13? Well, what's 4 times 13 mod 17? Where'd the 4 come from? Yes, the answer's got to be 1 because the 4 came from the chart. The 4 is the very special number that when multiplied by 13 and divided by then 17 gets remainder 1. So then when I pop this 13 in, it's going to turn it to remainder 13. And that's why this big number, which is 1526, if I look at it this way, I could see why it's remainder 5 when I divide by 13. But if I look at it this way, I can see why it's remainder 13 when I divide by 17. But that's not the smallest possible answer. Now, a smaller answer would be what I would get if I do 1526 minus 221. 221 is 13 times 17. See, if I add a multiple of 13, the remainder doesn't change. If I add a multiple of 17, the remainder doesn't change when I divide by 17. Sorry. If I add a multiple of 13 and divide by 13, the remainder doesn't change. Same thing for subtracting. If I subtract a multiple of 13 and divide by 13, the remainder doesn't change. If I subtract a multiple of 17 and divide by 17, the remainder doesn't change. So if I subtract a multiple of 13 times 17, which is 221, the remainder won't change if I divide by either 13 or 17. So if I do 1526 minus 221, I get 1305, which is an even smaller answer that's going to work. And if I subtract 221 again, I get 1054, which is even smaller. But I want to get down to the smallest possible. So what I do on the side is I do 1526 divided by 221. That 221 was 13 times 17. So on the side, I do 1526 divided by 221, and I get 6, remainder 200. And the 6 goes here. And the 200 goes there. I'm not done talking about this question. I'm going to write up these 9 numbers now and just do a little analysis again. Let me go to a new page for a sec. I'm going to rewrite the answer there. So it was 5, 10, 17, 13, 4, 13, plus, minus 6, 13, 17. That's 200. But let's take a look at it another way. If I mod this by 13, this and this won't contribute to the remainder because they both have 13s in them. All that matters is this, but this is remainder 1 because that's what the 10 gave us. So with this 5, it turns to remainder 5 just like I want. But if instead I take the 5, 10, 17, plus 13, 4, 13, minus 6, 13, 17, and I mod it by 17, well then this and this won't contribute to the remainder. This is all that will matter. If it were just the 4 and 13, it would be remainder 1, but the 13 in front turns to remainder 13, and that's why this 9 number thing gets us the answer that we need. The most important thing were those 2 numbers because those we needed a chart for. Everything else was easy to get. This is just the 2 mod numbers. This is the 2 remainders. These are the 2 mod numbers. This is just what I get when I divide the answer I have so far by the product of the 2 mod numbers. And then the answer is right here. So that is how this works. We have the video for this that you can rewatch this after. So I'm going to jump to, I like to end at 11. So I'm going to jump to the 3 equation process. Okay, we saw that. Talked about that. I think I have a bunch of practice questions here. Is that what we just did? Yes. Those are the steps. Okay, we are now ready to look at the 3 equation process. And would you do me a favor and write down on a piece of paper this 16 number kind of monstrosity. That one. Two times 5 times 7 plus 3 times 1 times 3 times 7 plus 2 times 1 times 3 times 7 minus 2 times 3 times 5 times 7. 16 numbers there. And we also have these 3 facts. These are just facts. It is a fact that 70 mod 3 is equal to 1. It's a fact that 21 mod 5 equals 1. And it's a fact that 15 mod 7. Those are just 3 facts that you can see are true. And that 70 is 2 times 5 times 7, is 21 is 1 times 3 times 7, and 15 is 1 times 3 times 5. So let's just take these 3 facts for a second and take a look now. I think I'll use highlighter for this so we can still kind of see through a little. Look at this question. It's saying, what's this giant 16 number expression if I divide by 3? What remainder would I get? Well, because there's a 3 here, that won't contribute to the remainder. And there's a 3 here, that term won't contribute to the remainder. And there's a 3 here, that term won't contribute to the remainder. So the only term that matters is this one. Well, look at this. You see the 257 here? That's actually the same as this 257. So according to this fact, this expression here without the 2 in front, but just the 257, that would be remainder 1. So then you throw this extra 2 in front, and you get remainder 2. On the other hand, if I were to take the same thing and mod it by 5, this term, and this term wouldn't contribute to the remainder because they all have 5s in them. And this 137, according to this, is remainder 1 when I divide by 5. So when I stick this 3 in front of it, this turns to remainder 3. And finally, if I divide by 7, this, and this won't impact the remainder at all because they all have 7s in them. So this is the only term that matters. But this 135, that's over here. That's remainder 1 when I divide by 7. So I throw this 2 in front of it, and I get 2. And what I end up with is a number that's remainder 2 when I divide by 3, remainder 3 when I divide by 5, remainder 2 when I divide by 7, which is the 23 number from before, because this big monstrosity of 16 numbers is actually just the number 23, the answer to the master-son problem. What number do I get if I get remainder 2 when I divide by 3, 3 when I divide by 5, and 2 when I divide by 7? What was my number? It was 23. Okay, here is how we are going to build this 16-number expression. And this is the big instructive question of the day. If you prefer to write the question this way, it's like a little bit more accurate to write it that way. But I sometimes write it this way so people get less confused. Oh, 23, no, I'm just telling you that it is 23. If you actually take this stuff and work it out, you would get 23, like 2 times 5 times 7 is 140, and 1 times 3 times 7 is 21 times 3 is 63, and 1 times 3 times 5 is 15, so that's 30. And 3 times 5 times 7, that's 105, so this is 210. And if you actually add these together, you get 233 minus 210 equals 23. So that's just what you would get if you took those 16 numbers and did that with it. The question is, where did these 16 numbers come from? You know, because that's what we're going to see. Once we get the 16 numbers, we'll be easily able to calculate it out. Okay, here it comes, and this is the primary part of today's lesson. And you know, there's 2 sections of this course. There's the math major section, which you're in, and there's the math teacher section. And the math teachers will not. The math teacher section won't learn the 3 equation process. I actually might not do the 2 equation process with them. They might do a different Chinese math topic. So this one's, let me take you through the 16. How am I going to build the 16 numbers? Well, I'm going to make 16 little slots. Okay, that's where my 16 numbers are going to go. I could actually fill in 9. I could fill in 12. How many slots will there be? For 3 equations, it's going to be 4 groups before, always. And for two equations, it's going to be 3 groups of 3. And if there were 4 equations, it would be 5 groups of 5. So it's going to be 4 groups of 4 in this case. In the case where it's a 3 conditions. I could actually fill in 12 of the 16 numbers right now. Why don't I do that? It's fun to do it this way. So the mod numbers go here, 3, 5, 7. That's going to be just like before. That's going to be used to adjust the answer to make it smaller. But this time, once we get our answer, our big answer, we want to make smaller answers that don't change the remainders when I divide by 3, 5, or 7. I'll put over here 2, 3, 2. Those are the 3 remainders. Actually, I could fill in 13 out of the 16 numbers before I even start doing any sort of calculation. Now, the next 6 we're going to put in this one, I'm going to put the 2 remainders, not including the 3. In this one, I'm sorry, not the remainders, the mod numbers. So I put 5 and 7. This one, I'm going to put the 2 mod numbers, not including the 5. Oops. And this one, I'm going to put the 2 mod numbers, not including the 7. So the remainder from the 3 is together with the other 2 numbers. And the remainder from the 5 is with the other 2 mod numbers. And the remainder from the 7 is with the other. So check this out. I have all except 4 of the 16 numbers filled in. But now it's the other 4 numbers, and primarily these 3 numbers that are the key. This 4th number is not going to be hard. This 4th number is just going to be like before. I'm going to take whatever this giant number is, because once I get these 3 yellow numbers put in, that's going to be like a big answer that's too big. And I'm going to divide by 105. Because subtracting 105 away or any multiple of 105 is not going to change the 3 remainders. So the green one's not a problem at all. That's just going to be dividing. It's these 3 yellow numbers. What needs to go in those yellow numbers are, we want to put a number here. Let's start with this one. I want to find a number here so that these 3 numbers multiplied together, I'm going to call this A, if you don't mind, just to call it something. So I want A times 5 times 7 to give me 1 mod 3. If I can do that, then I throw this 2 in front and I'll get 2 mod 3, which is what I want. I'm going to call this B. I want B times 3 times 7 to give me 1 when I'm modded by 5. That way, when I put this 3 in front, it becomes 3 mod 5, which is what I want. And for this guy, I want C times 3 times 5 is equal to 1 mod 7. Now, these A's, B's, and C's, we could do just in our heads. Like you could just literally say, okay, 5 times 7 is 35. Well, that's not remainder 1 when I divide by 3. But if I double it and get 70, well, 70, it is remainder 1 when I divide by 3. So A is 2. And 3 times 7 is 21. 21 divided by 5 already is remainder 1. So B is 1. And 3 times 5 is 15. 15 divided by 7 is already remainder 1. So C is 1 also. So I could actually work those 3 numbers out just through trial and error. It's kind of like before. We're trying to get this part to become remainder 1 when I divide by 3, 5, or 7. Well, to help us though, maybe these numbers get bigger. Maybe it's not 5 and 7, you know, maybe it's not 3, 5, and 7. Maybe it's 19 and 11 and 13. I'm not gonna be able to do it in my head. And that is where I made a series of charts, which are in the, so for instance, this this 5, 7 thing, here's where that answer is on a new set of charts. I go to, see this chart? I have a collection of 6 charts like this. Here's 2 of them. Here's 2 others. And here's the other 2. Now these charts will help us if the mod numbers are, the mod numbers for to use these charts have to be 2, 3, 2, 3, 5, 7, 11, or 13, which they are a lot of the time when I make these questions. And if they're not, I'll show you how to deal with that. Okay, here we are, everyone. Here's how to get this, this A. We're gonna go to the chart for n equals 3 and look for the 2 numbers 5 and 7. Check it out. So I go to the n equals 3 chart, and I take the 5 and the 7. Let's take the bigger number first, the 7 and the 5. And right there is my answer. This little chart tells me that if I take, listen carefully, if I take 7 times 5, I'll get 1 if I mod it by 3. Sorry. If I take 2 times 7 times 5, 2 times 7 times 5, mod 1, mod 3 will be remainder 1. So these numbers in these charts are what you'd have to multiply all 3. Like for instance, if I take 2 times 13, I multiply all 3 of those numbers, 2 times 13 times 11, and divide by 3, I'll get remainder 1. That's what all these numbers are. It's the third number. It's the thing you'd have to multiply both of those things by, all 3 together. The row name, the column name, and the number in the intersection, multiply all 3 of those together, and you'll get remainder 1 when you divide by whatever chart it's in. So you can see for the first one, 5, 7, 3 got me a 2, and that's why I put a 2 here. And for this one, I go to the 5 chart and go to 3, 7. I'll show you what that looks like. Here's the 5 chart. Here's the 3 and 7. Put the bigger one first, and there's a 1 there. And that's why B is 1. And then for this one, I go to the 7 chart and look up for 3 and 5. Here's the 7 chart. Here's the, do the bigger number, 5 and 3, and you get a 1 there. So now I have 2, 2, 5, 7, 3, 1, 3, 7, 2, 1, 3, 5. That all becomes 233. Wait, does it? I think so, yeah. And 233 is going to get me remainder 2 when I divide by 3, remainder 3 when I divide by 5, remainder 2 when I divide by 7. But to get a smaller answer, I need to subtract away 105. Or better yet, do 233 divided, sorry, do 105, which is 3 times 5 times 7 divided by 233, and get 2 remainder 23. And the 2 goes here, and the 23 is the answer. I think I have this written more nicely over, do I? Hold on. Here. It's written more nicely over here. Dawn, are you asking about when I subtracted the 210 to get the smaller answer? Mm-hmm. So because this thing became 233, that is an answer. That gets the right remainders, but it's not the smallest possible answer. So if I subtract away 233 minus 3 times 5 times 7, I'll get a smaller answer. 233 minus 105 is 128. 128 also works because if 233 divided by 3 gets me a remainder 2, subtracting by a multiple of 3 doesn't change that remainder. But subtracting by a multiple of 5 doesn't change the remainder when I divide by 5, and subtracting by 7 doesn't change the remainder when I divide by 7. So 128 is a small answer, and if I do 128 minus 3 times 5 times 7, I get 23, which is as small as I can get. Or I could do those two subtractions in one step by just dividing 233 by 105. And this too ends up being like, how many times can I subtract 105 away? And the remainder ends up being the answer to the whole question, because that's what's left. Now I have these charts, but I just wanted to show you that even if I didn't have these charts, like here, I want to show you how, let's say, where might this 6 come from? Well, that 6 is basically asking what times 7 times 5 will get me 1 when I mod by 11. That's where the 6. So in other words, 35 times what is equal to 1 mod 11? Well, that's a hard question. So I permit you to go to Wolfram Alpha. If you don't have the chart, or it's numbers that are other numbers besides, 11 and 13. And all I would have to do is say 35. I can't say 7 times 5. Say 35 inverse mod 11. And you see out comes the 6, which is exactly the same number that is in this chart over here. It should pop up in a second. It's exactly the same as that 6 there. Can you see the pointer? Because I wasn't sure if I do a screen share with the, do you guys see a little arrow moving around, like around the 6 right now? Oh, good. Okay, so that'll because I didn't even realize that. That's great. I can point to stuff that way. Yeah, I use the bigger number only because this whole chart would be symmetrical. Like there should also be like a 6 over here, but I should have just written it like that, and then it wouldn't be an issue. But since it's so symmetrical, I just put the 6 here. I didn't put 1 there. And that's what I wanted to show you today. Let me put up, here's another question. I'm just going to post it up on the screen to show you and talk through it. But then I'm going to end for today. I'll leave the Zoom session open if you want to talk to each other about it. So here's another question that's saying x mod 3 is 2, x mod 7 is 3, x mod 11 is 4. And the answer ends up becoming 59. And you can see here I have the 7, 11, no 3, the 3, 11, no 7, the 3, 7, no 11. Here are the remainders, 2, 3, 4. Here's the 3, 7, 11. This 2 came from the chart. I went into the 3 chart, looked up 7, 11, and got 2 there. Here I went to the 7 chart, looked up 3, 11, and got the 3 out of there. here's the 11 chart. I went and got the 3 and 7 to get the 10 there. This became a large number, which is 1445. I divided it by 231. That's 3 times 7 times 11 to get 6, remainder 59. So I'll leave that up here. I'm gonna stop the recording now, and I'll post this a little bit later.